Hi. So in today's video, we'll be looking at weak acid-base equilibria. We're going to be looking at what is the difference between a weak acid or a weak base and a strong acid or strong base. We will also be looking at how to do different calculations around solving the pH for a weak acid or weak base, and other things like calculating the pKa given certain information and also calculating the fraction dissociation. Alright, so let's get into the first question. So the first question is, what is the difference between a weak acid or a weak base and a strong acid or a strong base? So a strong acid is considered a strong acid because it fully dissociates. So if we look at this acid HA, we're saying it fully dissociates into H plus ions and A minus ions. And it has full dissociation. So that means whatever the concentration of your acid is, let's say 0.2 molar, we would have 0.2 molar of both the protons and the A minus anion because it would fully dissociate. So whenever we're trying to do a pH calculation, if we know the initial concentration of the strong acid, we can simply do pH is equal to negative log of that strong acid initial concentration because it's equal to the same thing as the concentration of the protons because it fully dissociates. But if we look at something like a weak acid, it doesn't fully dissociate. It actually partially dissociates. And we're going to say that by these double arrows going back and forth. There's an equilibrium going back and forth, and it doesn't fully dissociate, so we don't know how many protons there are in our solution. So even if we have 0.2 molar of this weak acid, let's call this one a weak acid, we don't know how much we have of the H plus proton. We also don't know how much we have of the A minus ion because it's a partial dissociation. So just doing pH is equal to the negative log of the weak acid's original concentration, right? This doesn't work because we don't know the concentration of the proton. Whereas in the strong acid, we knew that the concentration of the proton would be equal to the concentration of the initial acid. So that's the difference between a weak acid base and a strong acid or base. One fully dissociates and the other partially dissociates. So before we get into our questions, we have to assume a few things. We need to assume that all the protons coming from our weak acid is much greater than the protons coming from water. So we can ignore water autoionization. The contribution of protons from water is not significant, so we don't have to take that into consideration when we're calculating our pH. And we can say the same thing about the A minus ion. The contribution of the A minus ion is much greater than the OH minus from water, and we can ignore that as well. Also, we can assume that when our weak acid dissociates into a proton and its corresponding A minus ion, we can assume that it dissociates into equal parts H plus and equal parts A minus. So the concentration of A minus is roughly, or we're going to say essentially the same as the concentration of the protons. Next, let's look at what the Ka and the Kb is for a weak acid equilibria. So when we say Ka, we're talking about the equilibrium constant. And we know that the equilibrium constant is the concentration of the products over the concentration of the reactants. We also know that within our equilibrium constant, we ignore solids and liquids. So our Ka is the equilibrium constant for acids. So if we look at this reaction, HA, aqueous, it's going to turn into H plus, which is also aqueous, and A minus, which is aqueous, which means they're dissolved in water. Our Ka is going to be the concentration of the products, which is H plus and A minus, over the concentration of our initial, which was the products, HA. And we can see here that this is how you calculate the Ka. It's the concentration of the proton and the A minus over HA. And to get pKa, we just have to do the negative log of the Ka. And we would get a pKa. So it's important to realize here that there's an inverse relationship between our pKa and our Ka. And what I mean by this is a large Ka signifies a really strong acid, and a small pKa would signify a really strong acid. So there's an inverse relationship between the two. And why does a large Ka signify a strong acid? Well, if we look here, acid is determined by its contribution of protons to the solution. So if our H plus in our numerator was a very large number, infinitely large, our Ka would also be infinitely large. So that means a strong acid would have a really high Ka. So when we're looking at strong acids, they have a very large Ka value, and when we're looking at weak acids, they actually have a much smaller Ka value because they don't contribute too much when it comes to the H plus concentration. And when we look at our pKa, if you do the negative log of a Ka value, you're going to get an inverse relationship. So that's why the pKa is a really small number when our Ka is a really large number. And that's why there's an inverse relationship between the two. So next, let's look at how to calculate Kb. So Kb is the equilibrium constant for a weak base or a strong base. It's for bases. And let's do a reaction for a base. So we'll signify a base as B, and a base is added to water, which is a liquid. Base is aqueous. And we will be getting a BH plus because the base is going to be abstracting protons, and this is going to be aqueous, and OH minus, which will also be aqueous. So our equilibrium constant will be the concentration of the products over the concentration of the reactants. So OH minus and BH plus is on top, and the concentration of the base at the bottom. And we don't include water in our Kb because water is a liquid and liquids are not in an equilibrium expression. So we can see here that a large Kb would signify a very strong base because it would mean that there's a large OH concentration and it favors the reactant side. And that means a small pKb would mean a strong base. There's an inverse relationship. So next, let's look at how to calculate pKb given pKa. So it's important to note that pKw is equal to our pKa plus our pKb. And if you're given a pKa and you're asked to calculate the pKb, we know that pKw is 14, and so we can simply rearrange the equation 14 minus pKa, and that's going to give us pKb. And we know pKw is 14 because POH plus pH is going to equal pKw, and we say that it's equal to 14. Right? Also, if we're given pKb and we're asked to find pKa, we can do, again, 14 minus pKb, and we're going to get our pKa. It's very simple. And if we're given our Kw, we know that Kw is equal to our Ka times our Kb. So if you're given the equilibrium constant for an acid and you're asked to find the equilibrium constant for the base, we can rearrange the equation, Kw divided by Ka, and we will get our Kb. Likewise, if you need to find the Ka and you're given the Kb, rearrange the equation, and we can find Ka. And what is Kw? We know that Kw is equal to 1 times 10 to the negative 14. Okay, so let's look at our first question. Find the pH and fraction of dissociation of a 0.2 molar solution of weak acid with a Ka of 1 times 10 to the negative 5. So the first thing I like to do when we're given a question is to do a Rice table, specifically when we're trying to find the pH around a weak acid or a weak base. So R stands for reaction, I stands for the initial amounts, C stands for change, and E stands for equilibrium. So what is our reaction? Well, we have a weak acid, so we can use the weak acid reaction. HA is going to turn into H plus and A minus, right? It's going to dissociate. And what is our initial amounts? Well, since we're not given a volume, and we're assuming that the volume isn't going to change because we're in a flask and it's just a weak acid alone, we can be using molarity as our initial amounts instead of moles. Our initial concentration of our weak acid is 0.2 molar. We don't have any H plus or A minus yet. That's what we're assuming. And C stands for change. So we're assuming that there's going to be a change in the concentration of our HA. It's going to dissociate. So we're going to lose a certain amount of our HA concentration, but we would gain that as our protons and as our A minus. So our equilibrium would be 0.2 molar minus X. We would have X amount of H plus and an X amount of A minus. Okay? So once we get here, what do we do next? We know that Ka is going to be equal to the concentration of your H plus multiplied by the concentration of your A minus, and the bottom would be the concentration of your HA. We're given our Ka from our question stem, and we know now the algebraic values for our equation. Ka is going to be equal to the concentration of the protons, which is X, the concentration of the A minus, which is X, and the concentration of HA, which is going to be 0.2 minus X. So our equilibrium expression is saying that we have X amount of H plus and X amount of A minus, and we have 0.2 minus X amount of HA, and we know our Ka. So our final equation would look like this. 1 times 10 to the negative 5 is equal to X squared over 0.2 minus X. You can simply multiply the two X's because they're the same value. Okay, and our next goal is to solve for X. And how can we solve for X? Well, there's two ways we can solve for X. One way is we can use an approximation, and another way is we can use a quadratic formula. We have our equation 1 times 10 to the negative 5 is equal to X squared divided by 0.2 minus X. So let's start with our approximation method. So the approximation method is simply stating that in the denominator, our X value is so small we can ignore. So this X value is so small that we can ignore it in the denominator because it's not really going to take away from the value 0.2. So we'll assume that our equation now is 1 times 10 to the negative 5 is equal to X squared over 0.2. And the only way we can assume that X is so small that we can ignore it is if it is only less than 1% of the original concentration. And I'll get into that in a few minutes. So first, let's just solve for X using the approximation method. So given this equation, our final value of X would be equal to 0.2 multiplied by 1 times 10 to the negative 5, and it would be square rooted. And we would get a value of 1.41 times 10 to the negative 3. So we're saying that our weak acid has a concentration of 1.41 times 10 to the negative 3 protons when it dissociates. And to check if this approximation can be done, we use something called the 1% rule, and some classes may use the 5% rule, but for this video we'll be using the 1% rule. And what that means is we have to take our concentration of our X value, and we have to divide it by our HA, which is our initial concentration of the weak acid. So if this value times 100% is less than 1%, then we can approximate. But if it's not, then we have to use the quadratic formula. So 1.41 times 10 to the negative 3 divided by 0.2 times 100% will give us a value of 0.7%, and that is less than 1%. So in this situation, we can assume the value of X we calculated is an accurate value. Okay? So now that we have our value of X, we next have to find the pH. And the pH is simply the negative log of the X value, because our X value was our H plus proton. So the negative log of X would be the same thing as the negative log of our H plus value, and that will give us our pH. And the negative log of 1.41 times 10 to the negative 3 gives us a value of 2.85. Okay, so our pH is 2.85. And so the next part of our question is calculate the fraction of dissociation. We signify the fraction of dissociation by this letter alpha. So alpha would be our fraction of dissociation. And fraction of dissociation is simply asking us how much of the acid has dissociated. And it's just the concentration of our proton divided by the concentration of HA. So in our example, it would be our X value over our F value, but we don't multiply it by 100% like in the 1% rule. It's simply just the fraction of our H plus to our HA. And so this would be 1.41 times 10 to the negative 3, and our HA concentration was 0.2, and we get a fraction, an alpha value of 7.07 times 10 to the negative 3. And so this would be our fraction of dissociation, and our pH would be 2.85. So let's move on to our next question. A 0.054 molar solution of a weak acid HA is 0.6% dissociated. Calculate the pKa for this acid. So the first thing to realize is we're going to be assuming that our H plus value is our X. We're always going to assume that H plus is our X in these problems. And we know that X is going to be 0.6% of our initial solution, which was 0.054 molar. So 0.6% is 0.6 divided by 100. And we multiply that by 0.054. And we get a value of 3.24 times 10 to the negative 4. So we know that our X value is 3.24 times 10 to the negative 4 molar, which is the concentration of our protons, right? Because we simply calculated how much was dissociated from the initial concentration. The next thing to do is to calculate the pKa. So our Ka is equal to our H plus multiplied by our A minus all over HA. And we calculated that H plus was X. And we know that A minus will also be X since a weak acid dissociates into equal parts H plus and A minus. And our denominator will be our HA minus X after dissociation has occurred. And that further simplifies to X squared over HA minus X. So our Ka value is simply 3.24 times 10 to the negative 4 squared divided by 0.054 minus 3.24 times 10 to the negative 4. That will give us a value of 1.95 times 10 to the negative 6. Our negative log of the Ka will give us our pKa. So the negative log of 1.95 times 10 to the negative 6 is going to give us a value of 5.71. So the pKa for this acid that was 0.6% dissociated is 5.71. Okay, let's look at our next question. Calculate the pH of a 0.0035 molar CH3 NH2 solution. The Kb is 4.2 times 10 to the negative 4. So whenever we are asked to calculate the pH of a weak acid or a weak base, we always want to use a Rice table. In this situation, we're going to be using a Rice table for the weak base CH3NH2. We know it's a weak base because it's giving us a Kb value. The question is giving us a Kb value, and also CH3NH2 is a weak base. So let's begin with our Rice table. R is the reaction, I is the initial amount, C is the change in the concentration, and E is equilibrium. So our reaction for this situation, we'll be using B, which stands for the base, plus H2O, which is a liquid, will become BH plus because it'll be abstracting a proton from the water, plus OH minus because the base is creating OH in the solution. So we know that the initial amount of our base is 0.0035 molar. Again, we don't have to use moles in the Rice table because we're assuming our volume stays constant, so the moles will be the same amount the whole time. So we'll be using molarity for our rice table. Water, we can ignore that because it is not in our final equilibrium expression. The initial concentration of BH plus is 0, as well as the OH minus. The change stands for when there's a dissociation that occurs. So we're going to lose a certain amount of our B, our base, and we're going to be getting that as BH plus, and we'll also be creating OH minus, the same amount of OH minus in our solution. So our equilibrium values is 0.0035 minus x, x, and x. So the next step is to calculate our x value. Our x value can be calculated by using the Kb expression, which is equal to our concentration of our BH plus multiplied by our concentration of our OH minus all over our initial concentration of the base. We know that our concentration of BH plus is x, our concentration of our hydroxide ion is x, and the concentration of our base is 0.0035 minus x. This can further be simplified to x squared over 0.0035 minus x. And our Kb is 4.2 times 10 to the negative 4. So we'll set that equal to x squared over 0.0035 minus x. And the next step is to solve for x. So how do we solve for x? Again, we're either using the approximation method if it works, if it's less than the 1% rule that we're using, or if it's not less than the 1% rule, then we have to use the quadratic formula. So 4.2 times 10 to the negative 4 is equal to x squared divided by 0.0035 minus x. So if we use the approximation, we're assuming that this denominator x value right here is so small we can ignore. We're assuming that that value is so small it's not going to really change the initial concentration. So if we do that, our equation will be 4.2 times 10 to the negative 4 is equal to x squared over 0.0035. And if we solve for x, we see that x is going to be 4.2 times 10 to the negative 4 multiplied by 0.0035, and we're going to take the positive square root of that, and that's going to give us a value of 1.21 times 10 to the negative 3 molar. So next we have to check if we can use this x value. The way we check it is we do x divided by our base, the concentration of our x, divided by the concentration of our base, multiplied by 100%. And again, if it's less than 1%, we're good. But if it's greater than 1%, we're going to say it's not good. So 1.21 times 10 to the negative 3 divided by our base, which is 0.0035, initial concentration of the base, times 100% gives us a value of roughly 3%. And since this is greater than 1%, we cannot use the approximation. Okay, so since our x divided by b times 100% is greater than 1%, we're not going to be using the approximation. We have to be using the quadratic formula. Okay, how do we use the quadratic formula? Quadratic formula is pretty simple to set up. So the way we use the quadratic formula is by rearranging this equation. We're going to multiply both sides by 0.035 minus x. We see that the denominators will cancel out here, and we want to distribute this value. We're going to get an equation of 1.47 times 10 to the negative 6 minus 4.2 times 10 to the negative 4x is going to equal x squared. If we rearrange this equation to make it equal to 0, we're going to get x squared plus 4.2 times 10 to the negative 4x minus 1.47 times 10 to the negative 6 is going to equal 0. Next, we have to use the quadratic formula. We know the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we're going to be using that for this equation. So if we use that quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a, we'll have a final equation that looks like negative 4.2 times 10 to the negative 4 plus or minus the square root of 4.2 times 10 to the negative 4 squared minus 4 times a times our c, which is a negative 1.47 times 10 to the negative 6, all divided by 2 times a, which is 1. And we're going to get a value of x is going to equal 1.02 times 10 to the negative 3, or we're going to get a value of negative 1.44 times 10 to the negative 3. We ignore the negative value. It's not possible to get a negative x concentration, so we'll be just using the positive value. Okay, so we know that our x value is going to equal 1.02 times 10 to the negative 3, but this is not the H plus concentration, right? This is the OH concentration. So if we do the negative log of our x value, we're going to be getting our POH. So the negative log of 1.02 times 10 to the negative 3 will give us a value of 2.99. And since that's our POH, to get our pH, we have to do 14 minus our POH. So the pH will equal 14 minus 2.99, which will equal 11.01. So we can see that our weak base has a relatively high pH. Alright, so this is our last question, and I'd like you guys to try it out before I get into it. So the question is, calculate the hydronium concentration in a 0.005 molar hypochlorous acid solution, and it gives us the Ka of the solution. So the hydronium concentration is H3O plus, and that concentration is the same thing as asking us the proton concentration. Okay, and the first thing we want to do is we're looking at the fact that this is a weak acid, and it gives us a Ka of 3 times 10 to the negative 8. So we're going to start with a Rice table as usual, RICE. So for our reaction, we're going to still stick with our generic reaction, HA, and that's going to create H plus and A minus. Our initial concentration was 0.005 molar. We had 0 protons and 0 A minus in our solution. Then our change would be minus X, our gain would be plus X on the reactant sides. So our equilibrium concentration is 0.005 molar minus X, X, and X. So our Ka is simply our X times our X over HA minus that X value, which is X squared over 0.005 minus X. And that's going to be equal to 3 times 10 to the negative 8. So our goal is solve for X, and that's equal to our H3O plus concentration. So we just have to solve for X this time. Okay, so we know that there's two ways to solve for X. We can either use the approximation method, or we can use the quadratic formula. Depends if the approximation method works. So we'll start with the approximation method. So we'll approximate that X squared over 0.005 0.005 is going to equal 3 times 10 to the negative 8. So our next step is to solve for x. So x is going to be equal to 3 times 10 to the negative 8 multiplied by 0.005, and we're going to square root that answer and take the positive square root of it, and we're going to get a value of 1.22 times 10 to the negative 5. Again, to check if our approximation works, we have to divide this x value we got by our initial concentration and multiply by 100%. So 1.22 times 10 to the negative 5 divided by 0.005 multiplied by 100%, we get a value of 0.24%. And since this is less than a value of 1%, we can use the approximation method and assume that x is such a small value in the denominator that we can ignore it. And that means the x value we solve for is 1.22 times 10 to the negative 5 molar. That's going to be equal to our H plus concentration, which is the same thing as our H3O plus concentration. So if you like this video, make sure to subscribe, leave a comment, like the video, and have a good day.